Hi everyone, let's talk about acids and bases in the context of organic chemistry. As an example, let's talk about alcohols and phenols. And it turns out that both of these compounds, these class of compounds, can act as weak acids and as weak bases. An alcohol can act as a base by using its lone pair of electrons to attach to an acid, and that transfers over H+. This produces a protonated alcohol, where the oxygen makes 3 bonds and has a formal +1 charge. As an example of an acid, let's use a phenol. The phenol can donate its hydrogen and act as an acid. And so here we make the anion of the phenol, a phenolate, and we make water. But if we try the same thing with an alcohol, turns out it doesn't work so well. When we write the products, we get the anion of the alcohol and we make water, but it turns out that the anion of the alcohol is a strong enough base to remove the hydrogen from water, and the reaction reverses itself. We actually set up an equilibrium. And it turns out the equilibrium favors the left-hand side. Okay, how come? Why are phenols better acids than alcohols? Well, to understand this, we could look at pKa's. The pKa is a measure of acidity, and just like pH, the lower the pK, the more acidic it is, right? At low pHs, it's a very acidic solution. So if we look up on this chart where alcohols, here let's just use methanol, and phenol show up, they have very different pKa's. Now remember, pKa is a logarithm, right? So you take the logarithm of the equilibrium constant, and the log means, powers of 10. So if we round this up, well, let's round this down to 15, round this up to 10, and what we see here is that the pK is, rounding down here, so got some rounding errors here. We have a difference of 5, which means that's a difference of 10 to the 5th power, because the pK is a logarithm. And so 10 to the 5th power is 100,000. So a phenol is 100,000 times more acidic than an alcohol. Okay, why are phenols more acidic than alcohols? It's through resonance stabilization. We can draw resonance structures where the negative charge on the oxygen gets shared by the carbons of the benzene ring. And there's no resonance structure for the anion of methanol. Okay, and so since the benzene ring can kind of delocalize that negative charge and spread it out throughout the ring, that stabilizes the anion. Now how come the alcohol doesn't react readily with sodium hydroxide? Instead, we set up an equilibrium. Let's look at the pK values of the acids on both sides of the reaction. Here we have the alcohol, tert-butanol, serving as an acid. That's right here. Has a pK of 18. And then on the right-hand side, water serves as the acid. Right? Kind of follow the backwards arrow, the reverse arrow, and the anion of the alcohol is going to donate its electrons and attach to an H+. Right? So this is the base, and this is the acid from the point of view of the right-hand side going towards the left. Reactants changing the products. Okay, so water serves as the acid. Its pKa value is 15.74. And now let's round that up to 16. And so we can see that 18 differs from 16 by a power of 2, and that's 100. So it turns out that water is 100 times more acidic than tert-butanol. And so the equilibrium is going to favor the stronger acid. It also favors the stronger base. Okay, so what's going on there? If you think about the stability of the anion, and the more stable it is, it means the less basic it is, then you can predict basicity too. So let's try that again. If we look at the acids, water has a pK of 16, tert-butanol has a pK of 18. Okay, so pKa's are like pH. The lower the value, the more acidic. So water is a stronger acid. Why is it a stronger acid? Well, it just turns out that the anion it produces when water acts as an acid, it turns into hydroxide ion. And that hydroxide ion is a more stable anion than when tert-butanol turns into an anion. Tert-butanol is not a very strong acid, does not like giving up its H+, and one reason, or one way to understand that, is it doesn't like giving up the H+, because the anion it forms, it's not very stable. If it's not stable, that means it's reactive. So this is a stronger base compared to sodium hydroxide. Okay, so on the right-hand side then, we have the stronger base and the stronger acid, and then the reaction is going to favor going to the left to create the weaker acid and the weaker base. Okay, so here's one key idea. Stronger acids have more stable conjugate bases. Okay, let's look at the acidity of phenols. And on our chart, we got some phenols here. And look at their pKa's. They're going in decreasing order, going down. And just what we said before, the pK values, as they lower in value, they become stronger acids. Now, how are we going to be able to predict this? When we look at these different types of phenols, how do we know this is the order? Well, let's look at their differences. We got the original compound phenol, and then we got a bunch of groups at the para position. What are those groups? It's an amine, an alkyl group, a methyl group, that is, a chloro, a halide, and a nitro group. Those sound familiar. Yes, these are the ortho-para directing groups and meta-directing groups from electrophilic aromatic substitution. Hey, so memorizing those ortho-para directing groups is going to help us again to predict acid strength. And actually in a few minutes also help us predict base strength. So remember your ortho-para directing groups. The amine was a very strong activating ortho-para directing group. Alkyl groups were weakly activating. And those two type of groups made the reactions faster than benzene or unsubstituted benzene ring. The chlorine was a weak deactivator, but still ortho-para directing. And then we had the nitro group, which was a strong deactivator. A strong deactivator that directed to the meta positions. And why was that? Well, we said that the amines had lone pairs on the atom attached to the benzene ring. So in a resonance structure, the lone pair could create a double bond in one of those resonance structures. And effectively, it's supplying electrons to the ring. We call these type of groups electron donating groups. Other groups were deactivating, and these are the electron withdrawing groups. The halide is electronegative, and actually more electronegative than the attached carbon, and so it can pull electrons out of the ring, and it deactivates the ring. Oh, by the way, we said it was still ortho-para directing because it could create that additional resonance structure by forming a double bond using a lone pair. However, the nitro group was a strongly deactivating group because the atom attached to the ring, the nitrogen, bore a positive charge. And the pi electrons are then attracted outside the ring towards the nitrogen that's positive, and that would deactivate the ring. So the nitro group is still a deactivator, still electron withdrawing group when we talk about the acidity of the phenol. It's just that now this strong deactivating group, the metadirector, is actually helping the phenol become more acidic because we get this additional resonance structure where the positive charge on nitrogen can be adjacent to a lone pair on this carbon that bears a negative charge, and opposites attract. A very stable conjugate base. Okay, so keep reviewing your ortho-para directing groups and your meta-directing groups. We're going to use them for acid-base reactions and being able to predict the strongest acid. Now, you don't need a benzene ring like you do in phenol. We could look at some non-aromatic systems. So let's try and understand why this molecule is more acidic, lower pK value, than these two up here. Okay, let's look at the structures, and let's just consider the alcohol group here, the COH group, as our source of acidity. This hydrogen wants to get donated which means that the oxygen is going to become negative afterwards. The conjugate base will place a negative charge on the oxygen. And what's the difference between these molecules? Well, the bottom one, we got the CF3 group. The middle one, there's an extra methyl group. And the top one, there's 3 methyl groups. So in terms of electrophilic aromatic substitution reactions, how do these extra groups rate? Are they orthoparadirecting or metadirecting? Right, so CF3 was our metadirector, strongly deactivating. The methyl was weakly activating, orthoparadirecting. And if you have more methyls, that kind of helps activate it, right? They're kind of additive. So 2 weak activators has a net effect of being activating. So we got 3 activators here, and it's going to be orthoparadirecting. If we had an aromatic ring in an electrophilic aromatic substitution reaction, the methyl groups are activatings. They are electron donating groups, and the CF3 is still deactivating. It's electron withdrawing. So when this alcohol acts as an acid to turn into the conjugate base and place a negative charge on this oxygen, these 3 fluorines are creating a positive charge on the adjacent, well, on the carbon that's two bonds away, and opposites attract. The electrons are drawn towards this positive charge to help stabilize it, and that sort of siphons off the electron density. It withdraws the electron density and helps stabilize it. And that means that this hydrogen has an easier time of leaving. The pK is lower, it's more acidic. Now the opposite case is happening at the top. The methyl groups are actually pumping in electrons. And so when the anion forms, these methyl groups are pumping in more electron density. And that makes the negative charge even greater than a formal -1 charge. And so that's really unstable. Let's not use that word deactivating. It's very unstable, and it's making this molecule less acidic. Another way of thinking about it is that the anion that results is very rich in electrons, which should make it a good base. The opposite one, with the CF3 groups, it's pulling away the electrons. This is more electron poor, which makes it a poor base. Makes it a more stable molecule. It's not a very good base. Doesn't feel like doing anything. It's not very basic. Okay, it's more stable. And again, the more stable anion, the more stable conjugate base, makes for a stronger acid. Let's get to the heart of the matter. How are we going to be able to predict base strength? How are we going to rank these? How are we going to put them in order of acid and base strength? And I suggest let's look at basicity first. Right, so if we look at which anions are the most basic, so we said that the anion of tert-butanol is the strongest base on this list, that's going to make for the weakest acid. The most stable anion, and it turns out it's the p-nitrophenol, because of all these resonance structures, this is going to be the most stable anion, and it's going to make for the strongest acid. Okay, so if we can predict base strength from weakest to strongest base, all we have to do is flip it, and then we'll have the acid strength. In order to predict the order of basicity, first look at the atom that holds a negative charge. How stable is that atom with a negative charge? And you have to consider 2 things: electronegativity and the size of the atom. Second, let's look for resonance stabilization. Phenols can stabilize that anion, stabilize the base, makes it less basic. Consequently, the conjugate acid is stronger. Thirdly, look for electron withdrawing groups. You already know these. They're the metadirectors. And finally, if you're unable to make a ranking, like there's a tie between 2 molecules, look for similar acid-base reactions that you know, that we had to memorize. Look at those for some guidance. Okay, let's look at the nature of the atom bearing the charge. So the trend is, as the atoms become more electronegative, that makes for a more stable anion. And as you descend the table, the atoms get bigger. That also makes for a more stable anion. Okay, so let's start to make a little chart here, and let's begin with electronegativity. So fluorine's the most electronegative, and that row of elements on the periodic table are carbon, nitrogen, oxygen, fluorine. right? You get a periodic table exam, so you don't have to memorize it. Just go and grab it off the periodic table, CNOF. And then the trend is, as you create negative charges on these atoms, fluorine's going to be the most stable. If it's more stable, doesn't feel like doing anything, it's not very reactive. Carbon, on the other hand, not very electronegative. Oh boy, it's got a negative charge there. That's going to make it very reactive, very unstable. It's going to make it more basic. It wants to act as a base, get rid of that negative charge. Okay, let's descend the table. The most important atom of the list would be sulfur. As you go down, same column as oxygen, so it's somewhat electronegative, but now it's larger. It's going to be more stable. And so we might rank it in between oxygen and fluorine. Next, let's look at resonance. So let's look at the case where we have the anion of an alcohol and the anion of a carboxylic acid. Carboxylic acid. Yeah, probably that group's going to be more acidic. It's true, and that's because of resonance. It's not a difference between what atom's bearing the negative charge, because they're both oxygens, same electronegativity, same atom, but there's a resonance structure, where now the other oxygen atom can bear the negative charge. So the negative charge is spread across two atoms, and delocalizing it makes it more stable. You can also put phenols in here. Next, let's look at orthoparadirecting groups, really the metadirectors. So if we compare these two alcohols, which one should be more acidic? Well, the benzene ring is a weakly activating orthoparadirecting group, but the cyano group is a metadirector, a deactivating group. And so because it's deactivating, it's going to pull some electron density. And what's going to happen, it's going to remove some electron density to encourage this oxygen to donate H+ to become negative. Then there'll be more electron density to share. Or another way of thinking about it is once that negative charge is created on oxygen, the cyano group can remove that electron density and help stabilize it. The benzene ring, however, is an activating group. It's an electron donating group. It's going to pump in some electrons. And so that's going to make for a weaker acid because the anion is more reactive. The anion is more basic. Okay, finally, let's think about the anion of a triple bond. Where does that rank? Well, the atom bearing the charge is a carbon, so you might think about placing it way over here on the left. However, you'd be wrong. It actually is not more basic than nitrogen bearing a charge. You have to kind of remember some reactions. So how is the anion of a triple bond formed? Well, a common reagent is sodium amide. So the anion of a nitrogen is strong enough, it is more basic than a triple bond. This turns out to be a stronger acid. You got the stronger base forming a weaker base and a weaker acid. So we're thinking about putting the triple bond after the nitrogen. Should we also put it after the oxygen? No, because we said you could not form the anion of a triple bond with sodium hydroxide. So sodium hydroxide is not a strong enough base to remove this hydrogen. So we're going to have to put the triple bond right in between. So put it in the middle. Last thing to consider is that what are some typical carbon-centered anions? Those are your Grignards, Grignard reagent, MgBr, Gilman reagents, right, with copper. Those carbons have negative charges. N-butyl lithium is a very common base. Oh, if you saw the other halides show up, well, you're going to put them over here with fluorine. Okay, I hope this has been helpful because you're going to need to be aware of this. You have to always consider the possibility of acid and base reactions. And the reason why is they tend to be faster. And if they're faster and if it's possible they can occur, they probably will. So here's an example. Let's look at this reaction that someone wrote out. They want hydroxide ion to substitute with the bromine to form an alcohol. Looks pretty good. This is a primary halide. This is a good nucleophile. Looks like it's set up to do an SN2 reaction. But oops, at the other end of the molecule, we got the carboxylic acid group. So it turns out instead of the lone pair attacking this carbon, bumping out the halide, it's going to attack this hydrogen instead. So you're not going to get this product. Did anyone else consider the E2 reaction? Right, so there's a hydrogen over here that the anion could also attack and do an E2 reaction, make a double bond. Okay, that E2 reaction is still a possibility, but of these three, SN2, E2, and acid-base, the acid-base reaction is favored. They're just faster, and they just outcompete most other reactions. Okay, so I'll leave you with this last thought. How come acid-base reactions are so fast? And there's lots of reasons for this. One reason is that the solvent can play a role. So here's water with the hydronium ion in it. And it starts out with H plus at the bottom, and the H plus moves to the top of the page, but it's not the exact hydrogen ion that you initially started with, right? It's kind of hopping from water molecule to the other, and it's really not the same one. It's not really hopping either. It's just getting transferred. That positive charge is transferring through. Okay, and that speeds up the transfer of that H plus ion throughout a solution, especially if there's a negative charge at the top that's drawing that positive charge upward. It's going to make things much faster. All right, if you have more questions, come talk to me in class or in my office hour. Thank you.